Hello everyone. In the earlier topic on how CPU works, we have learned that the instructions and data are represented in the binary form at CPU and memory level. A program written in machine language is a sequence of instructions written in binary form. That means every instruction in the instruction set has a unique binary code specific to a particular CPU. A CPU having instruction size of 8 bits can accommodate up to 256, that means 2 to the power 8 different combinations of binary bit patterns. Each specific binary pattern is designed to handle a particular task in CPU, also called an instruction. That means a CPU having 8 bit instruction size can have 256 unique instructions. However, not all combinations are used by CPU designers. Some combinations are left for future use. Thus, the set of instructions so designed using a pattern of 1 and 0 form the machine language of the computer. Assume a microprocessor has a binary pattern 0011 1100 corresponding to an instruction that increments the current value of the accumulator register by 1. Another binary pattern 1000 then 0000 corresponds to an instruction that adds the contents of the register B to the contents of the accumulator register and stores the result back in the accumulator register. As explained earlier, it is tedious to remember and then write instructions in the binary language. These instructions are written in the hexadecimal format. For example, the hexadecimal equivalent of the earlier binary pattern for increment operation is say 0011 and 1100 is 3C. This instruction can be entered in the microprocessor kit by pressing two keys 3 and C. The monitor program of the microprocessor kit translates these hex codes into binary pattern and stores them in the specified memory location as configured by the microprocessor kit. The instructions written in the hexadecimal format provide little convenience as compared to the binary pattern, but it is still difficult to understand and write programs in hexadecimal format. The microprocessor kits used for writing machine language programs provide a facility so that the instructions and data are represented in hexadecimal format and stored in desired memory location through the available keyboard on the microprocessor kit. The address of the memory location is also represented using hexadecimal format. The handling of hexadecimal numbers used for representing instruction, address and data makes programming difficult to develop, understand and maintain. The software so developed is prone to errors. Therefore, each CPU manufacturer while designing a particular model of CPU has assigned a symbolic code to each instruction. These symbolic codes are called mnemonics. The mnemonics is based on a Greek keyword mindful, that is memory add. That means the mnemonic for an instruction consists of a word that suggests the operation performed by that instruction. In turn, it helps to easily memorize the instruction. For example, the binary pattern 0011 1100 as explained earlier is assigned a mnemonic INR A, which stands for increment the value of accumulator by 1. Similarly, the binary pattern 1000 0000 represented as 80 hex is assigned a mnemonic add B. As the mnemonic reflects the operation performed by the instruction, it clearly helps to memorize the instruction. The complete set of mnemonics for a particular CPU is called assembly language of that CPU. The mnemonics assigned to instruction set of one CPU varies as compared to the mnemonics assigned to the instruction set of another CPU. Therefore, a program written in assembly language for one CPU will not work over the other CPU unless the two CPUs are compatible at machine as well as the assembly level. Both machine and assembly language are microprocessor specific and are considered low level languages. The machine level language consists of binary patterns of instructions, data and addresses. The CPU only understands binary patterns. Therefore, a program written using mnemonics must be translated into machine code. An assembly language is a machine dependent programming language which represents each instruction using its mnemonic code and address using the labels defined in the program. The assembly language consists of English like words called mnemonics. Each statement in the assembly program is either an instruction mnemonic or a directive to the assembler to do a particular task. The facility of data declaration is also convenient as compared to writing the binary or hexadecimal equivalent of a number. However, an assembly program requires conversion to machine language program so that it can be executed by the CPU. Therefore, today we are going to study a special type of software called assembler. The assembler is a program that translates an assembly language program consisting of a number of assembly statements written using mnemonics and symbols in a text file into another program called machine language equivalent of the assembly program. The editor used for editing other text files can be used for writing an assembly language program in text format. The machine language so generated consists of a binary pattern of instructions understandable to the CPU system. Each CPU has its own assembler because the machine codes and mnemonics are specific to the CPU. In order to perform the conversion task by the assembler, it has to analyze the source program and find out the equivalent machine codes of all the mnemonic codes used, resolve the addresses represented as labels using actual physical addresses. The address reference made by the instruction for using operands or making a branch to a particular location is also resolved by an assembler. Using this information, the assembler synthesizes the machine language program so that it can be executed by the CPU. Compared to the machine language of a computer system, an assembly program provides the following to simplify programming. One is the facility of mnemonic operation codes. The mnemonic operation codes for machine instruction are easier to remember and use than the instruction opcodes represented in hexadecimal or binary format. The type of various mnemonics is smaller as compared to the number of instructions. For example, a single mnemonic move covers a large number of instructions between different pair of operands in a CPU. However, different opcodes in binary are used for movement of data between different register pairs in the machine language. The use of mnemonics also helps to detect invalid opcodes in the program. The second facility provided by the assembly language is the facility of symbolic operands. A programmer can associate symbolic names with data or instructions and use these symbolic names as operands in the assembly language program. The facility of assigning symbols to operands helps to relieve the programmer from worrying about the physical addresses and the changes in the physical addresses change later due to the change in the program. Another important facility in an assembly language program is the use of data declaration. The data can be declared in a variety of notations like binary, decimal or hexadecimal format. Representing a number say -31 in 2's complement form in machine language may be cumbersome. It will be represented as 1000001, but in an assembler specifying -31 wherever required is enough. In order to better understand an assembler, consider the format of an assembly language program. Typical format of an assembly statement is: first you write a label. Since the label is given in the square bracket, it is optional. Next is mnemonic operation code, and the mnemonic is followed by the operand specification. Again, one operand specification, you have another operand specification specified in square brackets, which indicate that it is the optional. An equivalent assembly language program could be loop add b followed by DECH jump if not 0 to loop followed by AND. See, consider these 4 lines of assembly language program. Thus, the specification of label and second and the subsequent operands is optional. If a label is defined in a statement, say loop in the statement, it is associated with a symbolic address corresponding to that statement. The address of all other statements is treated relative to that address of the label. For example, if a statement contains a label and its machine language equivalent is 3 bytes long, the next statement in the assembly program will be designated as having at address label plus 3. In the example of the assembly code, the instruction add b is 1 byte long. Therefore, the instruction DECH, which is the next instruction, is at loop plus 1 address. The instruction DECH decrement h is again 1 byte long. If more than one memory word is generated for a statement, and the label would be associated with the first of these memory words. Next is the operand specification. The operand specification in a typical assembly language statement has the syntax. The syntax is the operand specification starts with a symbolic name followed by plus or minus followed by displacement, and then in the brackets you have index register. Thus, the possible operand forms are, if you have an operand say memory area, you designate it is as with the symbol mem area. The mem area refers to the memory word with which the name mem area is associated. The operand mem area plus 5 refers to the word that is 5 words away from the word with the name mem area. Here, say in quotes you have written 5, it is the offset from the memory area. The operand in bracket 4 implies indexing the mem area with index register 4. That means, the operand address is computed by adding the contents of the index register 4 to the address of mem area. The operand mem area plus 5 followed by in bracket 4 is the combination of previous two specifications. Thus, various combinations of the addresses permit the assembly language programmer to use various addressing modes to the address operands. However, the language supports these combinations only if the underlying machine instruction set of the CPU supports all these addressing modes mentioned above. The third facility provided by the assembler is an facility of assembler directives. The assembler directive instructs the assembler to perform certain actions while assembling a program. Typically, in most of the assemblers, irrespective of the CPU design, the common names are assigned to the assembler directives. There are 5 commonly used assembler directives. They are first start, and third is DS, fourth is DC, and fifth is EQU. We describe the two directives start and end. The start again is followed by a constant. The start directive instructs the assembler to place the first word of the target program generated by it in the memory word having the address constant. The end again it follows by an operand specification which is optional. Normally the end indicates is a directive to the assembler that it is the end of the program. The end directive indicates the end of the source program. The optional operand specification indicates the execution of the program should begin with the instruction now, where the address is specified by the operand specification after the program has ended. The assembler directives DS and DC are declared as Again, the label should be there in the assembly language statement wherever you are using ds, and ds is followed with a constant. Again, the DC also should have the label first, and DC after that a value must follow the DC. The declarative storage, called DS in short, reserves an area of memory and associates a symbolic name with it as written in the label field. Consider the following DS statement: A followed by DS followed by 500. The statement reserves a memory area of 500 words in the memory. The label name is associated with the first word of the block of 500 words. A block is stored after 5 locations in the reserved memory area will be designated as A plus 5. Another declaration, declare constant, called DC in short, is used for defining constants. For example, the statement 5 DC and then in quotes you have written 5 associates the name 5 with the memory word containing the value 5. The programmer can specify constants in different representations: decimal, binary, hexadecimal. The assembler converts them to the appropriate representation for use in the machine instructions. The constants are used in the higher level language program are to be declared in a manner that later they can be modified in the program. The DC statement merely initializes the memory word to a specific value. The value can be modified by the program later as it is not protected by the assembler. An assembler or an assembly program handles the constant in two ways: as immediate operands in the instructions and as literals. The use of immediate operands require a special addressing mode in the computer. For example, consider the following assembly statement. This statement specifies that move immediate the contents of accumulator with a value 3C. The assembler would translate the above statement into an instruction with two operands A and another operand is 3C as immediate operand, which is used as a constant. Now, it initializes the accumulator register A with a value 3C. Now, the value 3C is protected and cannot be changed. A literal is an operand with a syntax equal to value. It differs from the DC statement that uses the value in that its location cannot be specified in the assembly program. The another assembler directive is EQU. The EQU directive has the following syntax. Again, it starts with a symbol followed by EQU followed by an address. The address is specified as a constant or a symbolic name referred earlier in the program as label, plus or minus for displacement. The EQU statement considers the defined symbol equivalent to the reference made on the right side mentioned as address. So, this is all about the facilities provided by the assembly language program over and above the facility provided in the machine language program. Next, we discuss how the assembler is organized. The organization of an assembler shows how it structures its analysis and code generation, which is synthesis task. In a single pass organization, an assembler program is converted into a target program on a statement by statement basis in one scan of the program from the first line till the bottom of the program. However, a single pass creates difficulty in code generation task. In a single pass assembler, the problem arises when an assembly statement refers to a symbol which is defined later in the program. This problem is called forward reference. The problem of forward reference is tackled by using a technique called backpatching. In this technique, the assembler replaces the undefined symbol with a blank value and stores the statement in a table of incomplete instructions. When that symbol definition comes later, it replaces the symbol with its actual reference. A multipass organization scans the program more than once to produce the target code and simplifies the code generation task. A 2-pass assembler scans the program twice. In the first phase, it does the analysis of the assembly program to perform the tasks such as check the syntax of the assembly statement, and if it is syntactically correct, separate the contents of label, mnemonic opcode and the operand fields of the statement. Second, if the symbol is present in the label field, enter the label field along with its relative location in the symbol table. Third, check if the mnemonic operand is available in the list of mnemonics in the mnemonic table. Fourth, calculate the relative address of the new statement by calculating the current size of the opcode and the operands in this statement. So, these are the 4 tasks performed in the first pass. In the second pass, the assembler does the following tasks for the synthesis of the machine codes. First is obtain the machine code corresponding to the mnemonic from the mnemonics table, obtain the relative address of each memory operand from the symbol table. Third is perform the task as directed by assembler directive. Fourth is generate the machine code and resolve address references with the relative addresses. So, this is all about the code generation task by an assembler using 1-pass and 2-pass assembler. Next, we talk about the cross assembler. A cross assembler is an assembler taking input from an assembly program designed for CPU X, and it generates a machine code equivalent for another CPU called Y. Such an assembler is called a cross assembler. So, in short, what we have learned today can be summarized as what is an assembler, how it works, typical uses of assembler and various design issues related to the assemblers.